Greetings to all viewers. This is Professor Ankit Singh. We'll now move to the next topic, that is design of rigid pavements. Okay. So what are the basic components of rigid or concrete pavements? You have the concrete slab, which is the surface layer. Okay. Then you have joints cut out. Okay. There are longitudinal joints which are a cutting along the roads. Okay, and transverse joint which is a cutting across the road. Okay, there are two types of cuttings that we provide in order to account for expansion and contraction of the concrete. Okay, we'll study in detail regarding the joints later on. Then in order to connect two slabs of concrete, okay, along the longitudinal direction or along the transverse joint, we have double bars. Okay, these double bars are reinforced steel bars. Okay, these are mild steel bars which are used in order to connect in the longitudinal direction, and then we have tie bars to connect any two slabs in the transverse direction. Okay, then under the surface course or the concrete slab we have the sub base or the base, and then later on we have the subgrade at the bottom. So what are the IRC guidelines for rigid pavements? As per IRC 58, there are different types of pavements: concrete pavements, jointed pavements. There can be continuous pavements also without any joints. You can have pre-stressed concrete also. Okay, so there are different types of concrete pavements which could be jointed or which could be continuous without any joints, and you can have reinforced or you can have plain concrete, and you can also have pre-stressed concrete. Okay, these are different types of concrete pavements that can be used. Guidelines for design of plain jointed rigid pavements for highways are provided in IRC 58 2002. Concrete pavements fail in different modes. Okay, so there are different failure conditions for concrete pavements. We need to consider those while we design the pavements. The failures that have been addressed in IRC 58 2002 version are load induced cracking, which could be either due to heavy loads or due to fatigue induced damage, and also thermal cracking. Okay, the cracking which is observed due to temperature changes. So what are the factors that will decide the design of pavement, design of rigid pavement? Firstly, we have the modulus of subgrade reaction. Okay, we have already discussed in detail regarding the modulus of subgrade reaction in module 4. Okay, we used plate load test in order to find out the value of capital K. Okay, so Westergaard considered the rigid pavement slab as a thin elastic plate resting on soil subgrade, which is assumed as a dense liquid. Okay, so the soil subgrade is assumed as a dense liquid. The upward reaction is assumed to be proportional to the deflection. Okay, so the reaction would be more as the deflection is more. Based on this assumption, Westergaard defined a modulus of subgrade reaction capital K in kg per centimeter cube given by delta K equal to P, where delta is the displacement level taken at 0.125 centimeters and P is the pressure sustained by the rigid plate of 75 centimeter dia. This is the standard plate, okay, of 75 centimeter dia at a deflection of 0.15 centimeters. Okay, so we conduct the plate load test using the standard plate of diameter 75 centimeters. Okay, then when there is a deflection of 0.125 centimeters at that reading, at that penetration, we take the load value, then we convert it into stress. Okay, so that stress is nothing but the that stress divided by 0.125 would give us the modulus of subgrade reaction. Okay, that is capital K. Then we have relative stiffness of slab to subgrade. Now what is this? A certain degree of resistance to slab deflection is offered by the subgrade. Okay, so the subgrade will offer some type of resistance to deflection. Okay, the subgrade deformation is same as the slab deflection. Okay, so the subgrade will deform in a similar fashion, however the slab which is placed over it will deflect. Hence the slab deflection is direct measurement of the magnitude of the subgrade pressure. Okay, this pressure deformation characteristics of rigid pavement lead Westergaard to define the term radius of relative stiffness, 1 in centimeters. Sorry, this is L. Okay, radius of relative stiffness is given by small l in centimeters. Okay, this is nothing but the radius of the portion which offers resistance to deflection. Okay, it is given by this equation. The equation is as follows: L is equal to whole root of 1 by 4 fourth root of EH cube divided by 12K into 1 minus mu square. Okay, where E is modulus of elasticity of concrete, H is the thickness of the slab, K is modulus of subgrade reaction, and mu is the Poisson's ratio. Okay, then we have critical load positions. Since the pavement slab has finite length and width, either the character or the intensity of maximum stress induced by the application of a given traffic load is dependent on the location of the load of the pavement surface. Okay, so we majorly consider 3 critical load positions. Okay, those positions are the corner, the edge, and the interior, or the interior portion. Okay, so there are 3 portions considered: corner, edge, and the interior. There are 3 typical locations, namely interior, edge, and corner, where different conditions of slab continuity exist. These locations are termed as critical load positions. Okay, so the slab may fail at any one of these positions due to loading at corner, due to loading at edge, or due to loading at interior, and it can also fail due to a combination of these 3. Okay, so the next term is equivalent radius of resisting section. When the interior part is loaded, only a small area of the pavement is resisting the bending moment of the plate. Okay, so whenever this interior part of the slab is being loaded, there is only a small portion. Okay, there is a small area which is resisting the bending. That radius, the radius of that area is nothing but the radius of resisting section. Okay, Westergaard gives a relation for equivalent radius of resisting section in centimeters in below equation. So this is the equation. B is the radius of resisting section. It is given as root of 1.6 a square plus h square minus 0.675 h when a is less than 1.724 h, and if a is equal to or greater than 1.724 h, then b is directly equal to a. Okay, so when you are going to find out the value of b, firstly you need to check whether a is greater than, equal to, or less than 1.724 h, and then according to this condition you need to use either this or this. Okay, so what is a here? A is the radius of the wheel load distribution in centimeters. H is the thickness of slab in centimeters. Now we have wheel load stresses as per Westergaard's stress equations. Okay, So what are the equations that Westergaard has given us to find out the stresses that develop at the concrete portion? The cement concrete slab is assumed to be homogeneous and to have uniform elastic properties, with vertical subgrade reaction being proportional to the deflection. This we've already understood. Westergaard developed equations for solution of load stresses at three critical regions of slab, that are interior, corner and edge. Okay, so there are different equations for each of these conditions, for interior, for corner and for edge. Interior, load in the interior and away from all the edges. At the edge, load applied on the edge away from the corners, load located on the bisector of the corner. Okay, so these are the three different equations that Westergaard has given us for stresses. So sigma I is stress at interior section. It is given by 0.316 into P divided by h square into 4 log 10 L by B plus 1.069. Then sigma E, that is at the edge, stress at edge, 0.572 P divided by h square into 4 log 10 L by B plus 0.359. Then corner stress 3P by h square into 1 minus A into root 2 divided by L whole raised to 0.6. Okay, so these are the three different equations that have been given by Westergaard. Now these were stresses developed due to loads. Now we have temperature stresses. Okay, so temperature stresses are developed in cement concrete pavement due to variation in slab temperature. This is caused by, there are few conditions for developing of the temperature stresses, which are daily variation resulting in temperature gradient across the thickness of the slab. Okay, so daily there is a temperature variation. There is different temperature in the daytime and different in the night time. Okay, and then we have seasonal variation resulting in overall change in the slab temperature. Now the temperature of slabs in the winters, in the summer, would be different. Okay, the former results in warping stresses and the latter in frictional stresses. So the daily variations would result in warping stress and seasonal variation would result in frictional stress. Now we will have a look at what is warping stress and what is frictional stress. So temperature stresses are of two types, warping and friction. Now the equations for warping stresses are all the three regions. Okay, that is interior region, edge and the corner region. We have three formulas. For the interior region, the equation is capital E into epsilon into T divided by 2 into Cx plus mu into Cy divided by 1 minus mu square. Okay, I'll explain the terms later on after I tell you about all these formulae. The second one is sigma Te, in which we consider the maximum value among these two. The first one is Cx capital E into epsilon into T divided by 2, or Cy capital E epsilon into T divided by 2. Okay, the maximum among these two values we would consider as the edge stress. Then for corner stress, capital E epsilon T divided by 3 into 1 minus mu into root of A divided by L. Okay, so here capital E is nothing but the warping stress, it is the modulus of elasticity of concrete, okay, in kg per centimeter square. Then we have epsilon, that is thermal coefficient of concrete. Then T, small t, is the temperature differential between the top and bottom of the slab. Mu is Poisson's ratio. Then what about Cx and Cy? Now these are, Cx is coefficient of direction along the x, which depends upon a ratio Lx by L, that I will discuss in detail while I solve the problems. Okay, so Cx and Cy are coefficients along direction x and direction y. Okay, now warping stresses in concrete slab when curling is restrained at different times. Okay, so what happens during the daytime? The temperature above the concrete slab is higher than the temperature at the lower portion. At that time the upper portion tends to expand and the lower portion tends to contract. So this is the shape that you would get if there is no restraint to change in shape. Okay, and this is at night time when the temperatures above are low and temperatures at the bottom are high. So there would be expansion at the bottom and contraction at the top. Now in both these conditions what would happen is you would develop compressive stresses at the top in this case and tensile stress at the bottom, and here you would develop tensile stress at the top and compressive stress at the bottom. Okay, this is warping stresses due to the daily variations. Okay, daytime and nighttime. Now due to seasonal variation in temperature we develop frictional stresses in the rigid pavement, which is given by a formula sigma F equal to W into L into F divided by 2 into 10 raised to 4. Okay, where W is unit weight of concrete, which is taken as 2400 kg per meter cube. Then capital L is spacing between the contraction joints, okay, or the slab length in meters, and F is the coefficient of friction at interface. A maximum value which is adopted is around 0.15. Then we have critical combination of stresses. Okay, so there might be presence of the critical combination, okay, of the stresses that could cause failure. Now what are the most critical conditions that we consider? We will discuss now. The cumulative effect of different stress give rise to the following three critical cases. There are three critical cases we consider. For summer in the midday, the critical stress is for edge region given by sigma critical is equal to sigma E, that is load stress at edge, sigma TE, that is warping stress at edge, minus sigma F, that is frictional stress. Okay. Then for winter midday, the critical combination of stress is for the edge region given by sigma critical equal to sigma edge load stress, sigma TE warping stress at edge, and sigma F, this is plus. Okay, so sigma E plus sigma TE plus sigma F, this is the last one is frictional stress. Okay, then we have at midnight condition, critical combination is for corner region and it is given by sigma critical equal to sigma C plus sigma TC. Okay, so this is stress due to load and stress due to warping stress. So the next concept is joints in rigid pavement. I'll start with this in my next lecture. Thank you.